Function simplification. Why do we need to simplify logic functions? Because simpler expressions uses less logic gates. This will lead to a cheaper circuit that represents the logic gate. Also, a circuit that consumes less power. We might end up with faster circuits. Sometimes, not all the time. Okay, simplification techniques. There are two simplification techniques. First of all, we have the algebraic simplification. By using the theorems and the postulates, the theories that we know already, we play with the function to get the simplest form of the function. This, of course, requires the skills on your part. You have to know the postulates and the theorems, and you know how to use them. But this technique will lead into an open-ended technique, meaning that there are no restrictions on the domain of the function. Whether it's 4 variables, 5 variables, 6 variables, there are no limitations on this. The other technique that is used is using the Karnoff map. And we will talk about this a little bit later. This is simplified standard forms only. You have to put the function in the standard form into the K-map. But this technique is limited to 5 variables. If you use more than 2 variables, this technique becomes harder. Okay, let's start with the algebraic simplifications for Boolean functions. What is the aim here in this simplification? We aim to reducing the number of letters and the number of terms. But achieving these two goals sometimes might be conflict. That means if you try to reduce, in some cases, if you try to reduce the number of literals, you might end up with a number of more terms and vice versa. In our study today, we will talk about minimizing the number of literals. Let's take the first example here. Assume that we have the function that is shown here for you. This function has 6 literals. We want to minimize it. Okay, we take these two terms here and expand them. X ended with X, we'll get this one. X, Y bar, or YX, which is this one, or with Y bar, which is this one. And this one goes down the same without any change. Now, X ended with X will lead to an X. From these two terms, if we take X out, then we are left with Y bar or with Y. And of course, this is equal to 1. And this one, Y ended with Y bar, will lead to a 0. This X here stays the same. And Y bar ORed with Y is equal to 1. And anything you end it with 1 is the thing, which is X. These two terms here, X and X, will lead to an X. And this one goes down as is. So this is the function in the product of sum form. If we want it to be in sum of product, then X ended with X bar, which is equal to 0, ORed with X ended with Z, which is equal to this. So this is the final minimal function for this one. You saw that we had before 6 literals in the function. We ended up with 2 literals in the function. Let's take example 2. Find the minimal sum of product and the product of some expressions for this function. Okay, if we take this term inside the brackets, we will get this term from the first one and take this one inside. So we get X bar, Y bar, X. This term stays the same. Now let's take a look at this one. This is of course equal to 0. Why? Because Y bar is equal to 0. So this is equal to 0. This stays the same and this stays the same. From these two terms, this one and this one, we take the Z out of the bracket. So we are left here with Y bar ORed with X bar Y. If we use the distribution law here, then we have Y ORed with Y bar ORed with Y, ended with this and is here, or it goes here, ended with X bar and Y bar, and this is equal to 1. This is equal to 1. So we are left with z ANDed with x bar ORed with y bar, which is this. If we take the z inside, then we have x bar z ORed with y bar z. Let's take example 3. Example 3. Minimize the following function. Okay, first we take this a inside, so we get ab ORed with ac. And we take this b inside, we get bb ORed with bc. Let's take these two terms together. AB ORed with AB is AB. And this is the same. Of course, this is equal to B. And this is the OR. And this stays the same. These two terms here are equal to B. B or BC, take the B out, so you're left with B ANDed with 1 ORed with C, which is 1. So this is equal to B. Now, if we take these two terms, this one and this one together, we will get a B. And this stays here, the same. So this is the function minimized in sum of product. If we want to have it in product of sum, we use the distribution here, B ORed with A, which gives me this, ANDed with, this is the AND here, B ORed with C, which is equal to this. Let's take example 4, minimize this function. Okay, if we take these two terms together and we apply the De Morgan's theorem, we have this side, and this is the OR becomes an and this one becomes this one. Okay, here we apply De Morgan's theorem. So what do we get? A bar ORed with B bar. We apply De Morgan's theorem here, we get A bar ORed with C bar. So what we have here is we have this term ANDed with A bar, and this is the OR, C bar ANDed with this term. Again, we apply the distribution law. So what we have is A ANDed with A bar is equal to A bar, ORed with A bar ANDed with B bar, which is equal to this. Okay, and we apply the same thing here. It's A bar C bar, ORed with C bar B bar, which is this, and this one here goes down same. Now these three terms here, they have A bar and A bar and A bar. So the OR of these together will be an A bar. And this here goes down, and this here goes down. Now if we take these two together, we take B bar out. From the two, we have B bar. We are left with C bar ORed with A bar C, which is this. Now we distribute the OR over the AND. We get C bar ORed with A bar, which is this, ANDed with, this is the AND here, C bar or C. And C bar or C is equal to 1. Now here, this is equal to 1. We take B bar inside, so what we get B bar C bar ORed with B bar A bar. If we take these two terms together, okay, A bar ORed A bar B, we get an A bar. And this goes down as is. And this here is the final minimized function in sum of product form. Example 5. Let's find out the minimal sum of product for this function. First, if we take these two terms, this one and this one, we take the b out, we are left with this. Now using the distribution law, we distribute and then we get this one. Of course, this term here is equal to 1. So we are left with AB ORed with B d bar. Now if we take these two terms, this one and this one together, this one and this one together, take the b out of these two terms, we are left with this one. Now distribute the OR over the AND, we get this. And this part of the term is equal to 1. And we are left with AB, which is equal to this, or with B C bar. Now if we take these two terms, this and this, which is this and this together, we will have this. Take the b out of these two, we are left with this. Now from De Morgan's theorem, this part of the term is equal to CD complemented. Now if we take these two terms, these two will lead to this. Now if we take these two terms together, we are left with AB. And this is CD and this is B. Now let's take these two terms together, the B and the AB, the B and the AB, they will lead to this. And this is the final end. Let's take a look at this example. Find the complement of this function and then show that the function ended with its complement is equal to 0. First, let's find the complement of this function. F bar is equal to this complemented. We apply the De Morgan's theorem here. So this is equal to X bar. This OR becomes an AND. And this is equal to YZ all bar. Okay, apply the De Morgan's theorem here. Take the complement inside. So this is Y bar ORed with Z bar. Now distribute the AND over the OR. So this is equal to X bar ANDed with Y bar ORed with X bar Z bar. Now let's find out what's F ANDed with F bar. This is F and this is F bar. Okay, notice that X ANDed with X bar is equal to 0. So this part of the term goes to 0. X ANDed with X bar goes to 0. So this is also equal to 0. Now if we AND this with this, we have Y ANDed with Y bar. That makes it equal to 0. Then we take this part, we AND it with this one. Here we have Z, and here we have Z bar. So the result is 0. So the final result is equal to 0. Now, F ANDed with the complement of F is equal to 0. This is general for whatever F is.